Okay. Hi again, for the network flow problems, minimum cost network flow problems. These are very special problem types, actually, and we see them a lot in different settings in our different problems that we're supposed to solve. And they have a very special structure. And due to their special structure, we will develop a specialized algorithm for that. And you'll see why, because life is a lot easier when we actually represent our problem like networks. So, first of all, let's understand its structure, right? Minimum cost network flow problem. It is the most fundamental of any kind of network flow problem that you can think about. So the basic idea is find the least cost shipment of a commodity, whatever it is, through a network. So we have some sort of a network. It can be wireless network, telecom networks, road networks, and you're supposed to send a commodity from suppliers to the demand points. Okay. There are many examples, many, and even we had certain examples when we were formulating in set one. We were distributing electricity, if I'm not mistaken. We then did some other transportation examples too. So, well, for example, think of a manufacturer trying to send from the factory to the warehouses. So we have suppliers, factories, we have warehouses, our distributors, and we have the road network as the network of that we're supposed to work on, right? Or flow of materials through various stations in a production line or in a telephone system, right? The applications of minimum cost network flow problem structure are a lot. So what is the idea? Okay, I have suppliers, I have demand, and there is a network. And I'm supposed to satisfy the demand from these suppliers over this network with minimum total cost. That's why it's minimum cost network flow problem, right? So the environment setting, the criteria, everything is set. Okay, so let's make more math on it, put more math on it. So we have a graph, okay, because we can represent our network as a graph. We have nodes of the graph and we have links on the graph, right? Those are like, so we have supplier nodes, we have demand nodes, and for each arc on that network, there is a cost, right? Because this minimum cost network flow problem. So there must be some sort of a cost for using the arc, going through, traversing the arc, okay? So the problem is that, okay, you have your demand, you have your supplies, you have your graph. The graph has arc costs for using that arc, and there may be capacities over those arcs. Now find me the least cost shipment structure over this network, okay? So for example, here we have, now there is a tendency that we keep using. So if the value B, each node has an associated B. B represents the net supply or net demand of the node. Yeah? So my factories, for example, are my suppliers, and my customers are my demand nodes, right? So we consider each demand node as with a negative B value, and each supply node with a positive B value. If the node is not a supply nor a demand, like Sivrisar, every road actually passes through that node. So it's just there because the network actually requires it. But it is not my factory, it is not my warehouse that I want to send to. So it may not be a demand or a supply, but just there because of the network requires it. Those nodes will have B as the value 0. So we assign, so we give actually each node to the demand and supply values. Okay? If it is negative, that means it requires. And if it is positive, that means it's going to send. All right, so for this network, for example, now our network node set is from 1 to 4. Our ages, as you see, look, there's an arc from 1 to 2. There's an arc from 1 to 3. There's an arc from 2 to 3, 2 to 4, and 3 to 4. All right? the representation of the notation is given like this. So for over each node, we represent the supply or demand of the node with the B value. And over each arc, we write the cost of using that arc and the capacity of that arc. Because it may be truck capacities assigned to there, or if it is telecom networks, there may be bandwidths that we could use. So we may have capacities. If we don't, then it will be infinity. For example, in this network, now look at our arc 1, 2. Apparently, the cost of using that arc per unit is $6, kilometers, whatever the metric we're using, and there is no capacity. On the other hand, the other arcs, as you see, like for example, arc 3, 4 can only be used for 10 units, and arc 1, 3 can only be used for 50 units because those are the total capacities. Now, in order for your problem to make sense, of course, your supplies should be equal to your demand. Otherwise, our problem will be infeasible, right? So we're going to assume that we will have a balanced network. So our factory output, our supply, total supply will be equal to our total demand. All right. Now, this is the formulation then. So go back to like when we were really having the lectures in the amphi, where we were formulating the problems, we were defining the variables, right? So I'm going to define a variable which will represent the amount of flow on the arc, xij, all right? And then with this variable definition, my objective function is clear. I want to minimize my total cost. Since I defined those C's as the per unit cost, okay, then my total cost is the total of the per unit cost multiplied with the amount that I'm sending through there, which is the decision. I don't know which arcs I'm using, and I don't know how many I'm shipping from where to where, right? So those are my decision variables. Okay, I want to minimize my total cost. Now, what is the thing I have to satisfy? What is the dynamics of my environment that I represent, that I should represent in my mathematical model? I have to make sure that I'm sending my supplies because there are demand out there, and I have to make sure that my demand is satisfied, right? And this is called flow balance, this constraint. Okay? And for each node I, you're supposed to write this constraint. For each node I, okay? So you pick a node, okay? And for this node, you look at the first sum here is anything that's getting out. These are xij's from I to j, right? And the other one, so this is out minus in, because this part is xji from j's to I, right? So this is out minus in. It's supposed to be equal to bi. If this is just Sivrisar, nobody wants anything, then if bi is 0, let me do it here. If bi is 0, this will say out equals in. Anything that enters to that node should leave because there is no supply, there is no demand, right? Now, if the node is a supply node, right, then my out will be equal to the total that I'm supplying. Yeah, that's what it says. For this node, if this is factor 1, then anything out, the summation xij from factor 1 will be the b of that factor. And if this is a demand node, then that's why for demand nodes, RBs are negative, because if this is a demand node, I must have enough coming in, right? So that's actually minus and out minus n equals bi. So that's absorbing that much of flow. That's why the flow balance ends with a negative for a demand node. And this is called flow balance constraint. And that's it. This is our MCNFP, minimum cost network flow problem. I'm minimizing my total cost, and I'm satisfying the balance over my network. How do I do that? From positive nodes, I'm dispatching my flows. The negative nodes are actually absorbing the flow. and the in-between nodes are actually letting them go through. Now, for example, this is also this is an example. Let me, so let's say, let me show you a feasible solution. Let's say this is a -10 and this is another -10, okay? That means I'm sending 20 units in here. Let's say this is a +5 and this is a +15. This guy, this is a 0, this is a 0. All right? Then what's happening? I will send 10 units to here, and 5 will go here, and 5 will go here. Okay? This 10 will come here, and then altogether 15 will go to there. For example, this is a feasible structure. I didn't draw you the network, but this is, with my demand and supply, a feasible solution if all capacities are infinity. Okay, this is my satisfying my flow balance. So here I'm sending out 10. Here 10 comes, 5, 10 goes, out minus n equals 0. Here 5 comes, 10 comes, 15, out 15, it's again 0. This is this is a +10. I made a mistake. I made a mistake. I made a mistake in the direction. So let's be these and let me these. Yeah. Now that's correct. Okay. And out minus n equals either total supply or total demand, depending on the B of the node. Any question? Because this is the basic, very basic structure. Then we will actually learn how to convert problems to this structure, because this is really special and handy. Any questions? Anybody want me to repeat any part, or are you all clear?
The last part.
Which part?
The part after you draw that examples.
Okay. So that was just a feasible structure. Okay, let me switch colors. I was trying to show you that out minus n equals the B in a feasible solution, okay? So I just made up an example. Here I have 2 suppliers, +10 and +10. I have 2 demand nodes. This 15 is actually for this guy. 2 demand nodes, -15 and -15. Okay, and everybody else, well, there are 2 other nodes, and their B values are 0. This is a -15, this is a 0, this is a 0. All right? So, for example, sending 10 units from here. I didn't draw the original network, by the way. I'm just sending, let's say there's supposed to be a network underneath this. I didn't draw that. I'm just drawing you the positive axis, the solution vector, a feasible solution vector. So this guy sends, this is a +10. So out minus in has to be equal to +10 for this. So there is no n, out equals to 10. This guy is a -5. So out minus in should be equal to 5 for this guy. Out minus in should be equal to 5. There is no out, and in is 5. So this is a -5, which is what I want, because this is a demand node. This is a 0. Out minus in should be equal. Out is 5 + 5. Minus in is a 10. So it's 0. This is what it is. So I'm just showing you the flow balance over a feasible solution. For this node again, out is 15, in is 10 and 5, which is 0 again for this node. For this guy, out is 0, in is 15, which is what I want, -15. This is flow balance. Okay, this is what this constraint says, because you're supposed to write it for all the nodes in your network. Here I have 1, 2, 3, 4, 5, 6 nodes. So I'm supposed to write 6 constraints for node 1, 2, 3, 4, 5, 6. Okay? Now, I told you these are like trucks, commodities, people, right? The examples. So the examples, we normally require integrality. Okay, so this is normally an example for an integer program. Oh, somebody is asking U. U is the upper bound. There may be like bandwidth or track capacity. So there may be an upper bound. If there is or not. If not, it's infinity. If there is an upper bound, your solution should obey the upper bound. Like you cannot send more than 10 units over this network because the upper bound of that arc is 10. Okay, you have to obey that. If it is there. In the example I draw there, I didn't put any. Now, I was talking here. So normally, the real-life requirements for MCNFP problems require that those X variables should be integer. Fine. So these are examples for integer models, right? But there is a very nice property for this structure with the flow balance and just upper bounds and mini cost flow, so MCNFP, okay? We call it total unimodularity. What do I mean is we forget about this integrality. We just give this to our solvers that you will be learning like Express, Cplex, whatever, Excel, all right? And we just give these to our solvers without declaring integrality. So we're going to treat these guys as they were linear programs and nicely, which is called LP relaxation, actually. So we solved the relaxed version of the problem, with just the LP version, and luckily, we end up with integer solutions. It's not luckily because actually MCNFP has a very important and nice property, which we call total unimodularity. It's a very strong property. We won't be dealing with proving it or anything, but I want you to learn that. So you can forget about integrality in MCNFP structure, and your results will always be integer if your data is integer. All right? This is a very strong property of the MCNFP models. Okay, then, now, remember this structure, okay? Minimize total cost, subject to flow balance, and upper bounds of the arcs if there is any. If you can end up with this structure, I keep telling it's a nice structure, and you will be having fast results for your models. So what we will be doing from now on for a while is I'll try to guide you to a mindset where, given a problem, how can we convert this so that at the end our model will look like MCNFP? Okay? That's what I'm trying to do right now, which is pretty crucial, actually. So for certain problems, not all of them, of course, but for certain problems, even though it's not very apparent, you may treat them, you may convert them to MCNFP, and that's what we will be doing, okay? Formulation as an MCNFP. Steps. We will have 3 steps. We need to come up with a network because it requires a network. Then we have to find our B, C, and U, the parameters that the environment setting for us. And then we will see that, okay, if I solve MCNFP over this problem I created, my result will actually give me the solution for the problem at my head, which I'm trying to do. This will be clearer after I do one example with you. Consider the assignment problem, okay? We formulated this in set 2 when we are actually formulating integer and when we were teaching you integers, binary variables and everything, okay? Assignment, we have n jobs and people. So who should do what is the original problem. We defined an xij variable for that. We're saying that if I is assigned to job j, that was a 1, and if not, that was a 0. And this was our formulation at the very beginning, right? This is what we do. We minimize the total cost, and we made sure that each person gets a job, and each job is done. This was the thing we did when we were actually formulating in set 2. Okay? Now, so keep this in one hand in your mind. Now we will create a network. then we will apply these steps. We will form a network. We will find B, C, and U, and then we will just write the MCNFP formulation. And at the end of that formulation, we're actually going to get assignment of people to jobs. Okay? All right, let's do that. Formulation as an MCNFP. I need a network, right? Okay. So I have my people, even though it's there, let me put it like this: person 1, person 2, up to person N, and job 1, job 2, up to job N. So now I'm creating my network. I'm making up a network which is specific for this problem. Now the arcs are like this. And over each arc, say, if person 1 cannot perform a job, then I don't put that arc, yeah? Or I put an infinity there as a cost. Now I'm going to write the cost of, so C11. I know that cost of assigning job 1 to person 1. I already have it in my original problem structure, right? If person I is assigned to job J, then the cost is Cij. That was given to us. So what I'm going to do is, so there is a PI in here, and there is a job J in there. So this thingy will say Cij. Okay. Now, I did create a network with my nodes. So now I have to determine supplies and demands. I have defined the cost. I have to determine supplies and demands and upper bounds. Those are the things that are left. Remember, let's go back to the formula. Okay, form the network. I did form the network. Step 2, provide B, C, U. C is done. I'm supposed to find B and U. Now think about it. B is actually total demand and total supply, right? So what can a person supply? How many jobs can he do? 1. So each person will have a +1, right? And each job is a -1. Each job has to be done. So if a person sends 1 unit to a job, that means that person is going to do that job. That's the output, right? So then my B's are done too. My persons are +1. My jobs are -1. Now upper bound is like how many units can I send from my suppliers to demand? Well, that's 1 for this example because it is when the person performs the job, right? There is no other thingy. So my UIJs are 1. So my BIs are done, Cij is as given, and my U's is just 1. Now, think about it. If I solve this problem over this network I just created, minimize total Cij, Xij, subject to, well, each persons will get out with 1, each jobs will have -1. So if, let's say, my cardinality of site N is, let's say, 20, I require 20 in here, 20 in here, 40 constraints in here. Okay? Each person will say 1, send 1. Each customer will receive 1, right? So 20 from there, 20 from there, because my node set is actually my persons and my jobs. Yeah? So this is not actually my cardinality. If cardinality P is 20, cardinality J 20, my cardinality of overall network is actually 40, right? I have to write 40 constraints. And if I solve this problem, meaning my Cij, Xij, subject to each person should send 1 unit, each job should receive 1 unit, and the R capacities are 1, at the end, I will get a solution where each person and job is actually assigned. Yeah? Because each person should send something, each job should receive something, out minus N should be equal to either +1 or -1. I don't have any other nodes on this network anyway. I only have demands and supplies. I made my network. I made it up. Yeah. So when you think about it, for supply nodes, let me. So this is the objective function, right? Cij, xij. Then for my supply nodes, which means my persons, my summation xij should be equal to 1 when I is in the person set. And summation xij, this is over j, this is over I, equals to 1 when this is xji then, okay? If j is in the, from j to I, demand set. And this is my formulation I did at the very beginning, yeah? Summation xij equals to 1, summation xij equals to 1. And if you look at it, this is out minus in. So out minus in, this is what it does, right? So that actually finishes our step 3. Any questions? I know this is a different mindset. It requires some thinking, but believe me, after a while, you will appreciate the way to look at the problems from a network perspective. You don't have to. You can formulate assignment as assignment, right? We did that in set 2. This is our assignment formulation. But now I'm showing you that we could actually come up with a network and formulate this as an MCNFP formulation. Why? Because now, this problem has, for example, unimodularity. Now, in the previous case, you should require your binaries. Right? In our original formulation, I have to declare them as binary variables. But now in the MCNFP, I told you we could forget about integrality because it's unimodular. So I formulate this as an MCNFP, and my life is easier. Okay? Oktay, there is no second constraint. There is only one flow balance.
Hocam buraya çevirirken vardı ya 2 tane.
Yeah, that is actually out minus n equals bi. Yeah. So if bi equals to +1, that means that is my supply node, my person. So for persons out, which is xij, there is no n equals +1. Sum over j if I is in the person set. Now, if bi is -1, that means this is a job, right? It's supplying. So there is no out from jobs, but there are ins to jobs. So I will sum over j i's over j will be equal to -1 if I is in the job set. Well, these minuses will cancel out, so it's the same thing, right? And this is actually what you have written in the assignment version. I did that to show you actually the constraints are actually the same. When you write flow balance for persons and jobs separately, you're going to write this and that. You don't have, because it says pick an I, and for that I, write the flow balance. Now, if my I is in the person set, this is what I'm going to write. If my I is in my job set, this is what I'm going to write. And there is no other I, because I made up, and in my network, I either have persons or jobs. There is no other I. That's what I was trying to show. Is it clearer now?
Yes, hocam, thank you.
Welcome. Any other questions? Because I'm trying to explain these in a slower pace because these are really crucial, and I know this is a different mindset. So even though in the original problem there was no network, right? Sometimes network is there. There is this road network, there is this telecom network. So the MCNFP is very apparent. But sometimes for certain applications like this assignment problem, there is no network. But we can create a network and solve and assign appropriate parameters so that solving MCNFP over this created network will actually solve my assignment problem. Why did I do that? I repeat, in the assignment problem, yes, okay, life seems to be okay, but I need to define, for example, my binary variables. I have to tell the model that these are binary. But if I consider it, if I observe that this looks like MCNFP, I can forget about integrality and just give them as like this. My UIJs are 1, right? And my BIs are either +1 or -1, depending on the structure.